we've spent some time over the last several days talking about the photoelectric effect. Photoelectric effect says when light, or a photon, when a photon strikes a metal, then sometimes an electron is ejected. Not always. That photon has to be above the threshold frequency or above the work function or below the threshold wavelength. But if that condition is met, then an electron will be ejected. In 1908, it was observed that if that photon was way, way, way above the threshold frequency, in other words, that photon was in the range maybe of X-rays, then we would get a phenomenon called the Compton Effect. The Compton Effect says when light, like an X-ray photon, strikes a metal, an electron is ejected, but you sometimes get a second photon ejected as well. Now, classical theory, or old-style physics, we'll define classical theory as pre-Einstein. Quantum theory, post-Einstein. Classical theory, pre-Einstein theory, would say that if a photon strikes the metal and an electron is ejected and a photon comes out of it, then it must be the same photon as the original photon. When I throw a rock at a big block of ice, sometimes a little chunk of ice breaks off. But the rock that bounces off is the same rock as I started with, right? Does that make sense? So classical theory would predict that if a photon strikes this metal and an electron is ejected, then the photon that comes back out of it must be the same energy, or must be the same photon as we started with. But that wasn't what the observation showed. The observation showed that that photon that came out of it was less energetic than the first photon. So in other words, if you started with a photon that was visible light, X-rays, maybe you end up now with a photon that's in the range of ultraviolet. That second photon was less energetic than the first photon, therefore it was a different type. Now, if we go back to the rock and ice analogy for a second, it actually kind of works. When you throw a rock at this big chunk of ice and a little chunk of ice breaks off, that's the electron that's been ejected, and the rock bounces back, it's the same rock, but that rock is going to be less energetic than it was in the first place. That just means that the rock is going to be moving not as fast, right? But when we're talking about the energy of photons, the energy isn't related to the speed, it's related to the type. So the rock is less energetic than the first rock was. So is the photon. But the rock being less energetic means it's moving slower. The photon being less energetic means that it's going to be a different type of EMR, a smaller frequency of EMR. So the Compton effect just says when light strikes a metal, a second photon, which is less energetic than the first photon, is emitted. Classical theory predicted that the frequency would be the same. In other words, you'd end up with the same photon as you started with. But quantum theory, or Compton's explanation that used photon theory, said that no, it wouldn't be the same. It would be less, a smaller frequency than the original photon because it had to have a lower energy. Now, Compton explained this by saying that this is really just a collision. It's a collision, like two cars collide, or two baseballs collide, or two people collide. It's really just a collision between a photon and an electron. What do we do when we have a collision? Like, think back to week 2 of Physics 30. What do you do when we have a collision? Momentum, conservation of momentum, right? So Compton said, this is really just a collision in which momentum and energy are conserved. But there's a problem with that. How do you deal with conservation of momentum when you're talking about a collision between a photon with no mass and an electron? How can momentum be conserved when something with no mass causes something with mass to move? That's the big takeaway from this. Okay, that's the big qualitative takeaway from the Compton effect for you. And that is that photons, despite the fact that they have no mass, photons have momentum. And I'm going to justify that for you in just a second. But for now, I want you to remember that that's the big takeaway. Photons have momentum. Even though they don't have any mass, and you think they need mass to have momentum because P equals m times v, they still have momentum. Let's justify that now. Let's justify the fact that photons have momentum. We know that from day one of physics 30, the momentum of an object is equal to m times v. But this is our problem, right? This is our apparent contradiction with this whole thing, is that photons don't have any mass. But photons do have energy. And Einstein said in 1905 that energy and mass are two different forms of the same thing. It's kind of like ice and liquid water. Ice and liquid water are two different forms of the same thing. You can change ice to water, and you can change water to ice. They're not exactly the same thing, but they're two different forms of the same thing. How much water do you have in that cup? I got none. I got ice. Well, okay, I have a certain amount of equivalent water because the ice could be converted to water sometime down the road. Or how much ice do you have in that cup? Well, none. I got a bunch of water. Well, okay, you have equivalent ice because you can convert that water to ice sometime down the road. Ice and water are two different forms of the same thing. Einstein said that energy and mass are two different forms of the same thing. And you can convert energy to mass, and you can convert mass to energy. And you can convert them by an equation, probably the most famous physics equation ever, one of the least understood physics equations ever. Which one am I talking about? Good. E is equal to mc squared. Einstein said that if you have a certain amount of mass and you multiply it by the speed of light squared, then you get the equivalent energy. Not how much energy you have, but how much energy that mass is worth, basically. Right? If it was energy, this is how much energy you'd have. I got this much mass, but if I had the energy, this is the amount that I would have. Now, similarly, we can rearrange this to solve for equivalent mass. You get E over c squared. So if a photon has energy, if we divide that amount of energy by c squared, we get a certain amount of mass. It's not really how much mass the photon has. It's called equivalent mass. It's how much mass the photon would have if it had energy. Right? It's how much water you would have in that cup if that ice all melted. So what Compton did is took this equation, Einstein's equation for equivalent mass, and subbed it in to P is equal to m times v. And he gets this, E over c squared times v. But what is v in the context of a photon? Speed of light. So it would be c. E over c squared times c. Let's cancel out the c and the c. We're left with P is equal to E over c. The momentum of a photon is equal to the energy of a photon divided by c. So now we have a way of calculating the momentum of a photon without the need for photons to have any mass. Now, on your data sheet, you're going to see this rearranged. It's going to look like this. E is equal to P times c. The energy of a photon is equal to the momentum of a photon times the speed of light. Now let's take this equation, P is equal to E over C, and do a substitution. Let's replace E with H times F, because the energy of a photon is H times F, right? Divided by C. Let's replace E with HC over lambda. This equation, by the way, is on your data sheet as well. The momentum of a photon, HF over C isn't, H over lambda is. The momentum of a photon is equal to Planck's constant over the wavelength. And there's one more equation that also appears on your equation sheet in the context of photon momentum, Compton Effect photon momentum. It's an ugly looking one, but it's not nearly as bad as it seems. Delta lambda is equal to H over MC times 1 minus cosine theta. All of these equations, by the way, that are boxed off in red appear in the top right-hand corner of your data sheet under quantum mechanics in nuclear physics. E is the energy of a photon. P is the momentum of a photon. C is the speed of light, 3 times 10 to the 8 meters per second. This is the photon momentum. The wavelength of the EMR. This is Planck's constant. What value do you think you're going to use for Planck's constant? If you're not sure, go 6.63. In fact, you got to use 6.63 here. Just like with 1F mv squared or QV stop, you got to use 6.63. Same thing down here. This would be the change in wavelength, by the way. If we lose energy in this photon, the photon loses energy. Remember, the second photon is less energetic than the first. Then it gains wavelength. So it's the increase in wavelength of the photon. Planck's constant, the mass of the electron, the speed of light. Theta is the scattering angle of the photon. So the photon, the X-ray strikes the metal, and the electron is ejected. The second less energetic photon is also ejected. At what angle does it come out at? That's theta, the scattering angle of that second less energetic photon. First example. This one's from the board, not photocopied for you because it's the only one that you have to copy out. The next one's from your textbook. So I'll ask you to copy this one. It says, calculate the energy and the momentum of a photon whose wavelength is 600 nanometers. All of those equations in the top right-hand corner of your data sheet are for photon momentum, the Compton effect, photon momentum. The one that I'm going to use to find the momentum of a photon is equal to h. It says momentum is equal to h over lambda. It's 6.63 times 10 to the minus 34 because we always use joules in the context of photon momentum, divided by 600 times 10 to the minus 9. We're going to crunch those numbers here, see what we get. 6.63 times 10 to the minus 34 divided by 600 times 10 to the minus 9. I get 1.105 times 10 to the minus 27, or 1.11 times 10 to the minus 27. What would the units be here? What was it back in Unit 1? Kilograms meters per second. It's odd to have kilograms in your units for a photon that doesn't have any mass, but it is what it is. Now, you want to find the energy? There's two ways to find the energy. We could say energy is equal to, what's one way? Momentum times the speed of light? Yeah, that works. The other way to find the energy is what? Take this momentum and multiply it by the speed of light. The other way to find energy is, what would you have done last week if I asked you to find the energy of this photon? 1F mv squared? No, because that's kinetic energy of something with mass. HF, or in this case, HC over lambda, right? Either way you look at it, you're going to get the same answer. And that answer is 3.32 times 10 to the minus 19 joules. Just because we've moved on and we're now talking about photon momentum doesn't mean the equations that we learned last week for photons aren't valid anymore. It just means that we've got another option here. Last one for the day here, and then I'm done, finally. X-ray photon of wavelength 0.05 nanometers scatters at an angle of 30 degrees. What's the wavelength of the scattered photon? What I want to do here is first find delta lambda. It's h over mc times 1 minus cosine theta. It's 6.63 times 10 to the minus 34 divided by 9.11 times 10 to the minus 31 times 3 times 10 to the 8. those are all constants on your data sheet, times 1 minus cosine 30 degrees. Now let's figure out what that is. H over mc, 6.63 times 10 to the minus 34 divided by the mass of the electron times the speed of light gives me 2.42 times 10 minus 12. Times that by 1 minus cosine 30 gives me 3.25 times 10 to the minus 13 meters. Done? That was easy enough, right? Except it's not done. What have I just found? No. What is it, Brandon? Change in wavelength. What am I looking for? The final wavelength, right? Here's the initial. Here's the change. What's the final? I'm going to say delta lambda is equal to lambda f minus lambda I, and lambda f is therefore equal to delta lambda plus lambda I. So what I just found there, 3.25 plus the initial wavelength, 0.05 nanometers. I get 5.03 times 10 to the minus 11. Okay? So even that one's not nearly as bad as it seems, eh? If you're solving for theta, it's a bit trickier, but honestly, I can't recall a time when you've been asked to solve for theta. So I wouldn't worry too much about that. There are a couple questions that go with this. I'll put this back in a second to let you guys finish copying that. But I just want to point out the questions that go with this. They are on page 723 and page 724. There's 4 questions there, though. They should go fairly quickly for us. I'm going to post at the end of the day a diffraction and interference quiz. I'm not going to give you that quiz tomorrow. I'm just going to post it, and you guys can work on it at your leisure before your test on Wednesday, just for practice. I'll also do the same with the photoelectric effect. Okay, your practice question set and your quiz on the photoelectric effect that you guys can work on at your leisure, not for marks, but just in preparation for the test. And you can let me know if you have any questions. Of course, tomorrow your unit assignment is due.